All right, so we've spent some time talking about how we can model heat transfer that happens between two different objects. We've also spent some time talking about how we can model heat transfer that happens inside of an object. And given the fact that we have these two different ways of modeling heat transfer, it makes sense for us to try to deploy the two equations that we developed to understanding a physical system where both of those modeling techniques are relevant, right? Where we can use both of those equations to get meaningful information about how a common system that we see in our day-to-day lives, a common thermodynamical system, behaves. And perhaps one of the simplest and most common systems of this type is a wall, right? An insulating wall. And so what we're going to work on now is on trying to use both of the equations that we developed to understand heat transfer that happens through walls. So here's the physical scenario that we're working with. Let's suppose that I have this brick wall right here, which has a thermal conductivity of 0.6 watts per meter degree Celsius. All right? This brick wall, you can imagine, is maybe separating some room on the left from the environment, from outside. Okay? This brick wall has a thickness of 0.25 meters, and it has a cross-sectional area of 10 meters squared. All right? And we know certain things about what the temperature looks like inside of this wall, which is that the left side of this wall is at a constant fixed 20 degrees Celsius, and that the temperature gradient in this wall in the x direction, which we've defined to be, to the right, that the temperature gradient is negative 80 degrees Celsius per meter. Now, how do we parse that statement, right, that the temperature gradient is negative 80 degrees Celsius per meter? Well, what you can imagine is that as you move from left to right inside of this wall, for every meter that you move to the right, the temperature is going to drop 80 degrees Celsius. That's kind of what this means. Okay? Now, the wall is not, a meter long, but you can also think of it as saying that for every 0.1 meters that I move to the right inside of this wall, the temperature is going to drop 8 degrees Celsius. All right? And that this is true everywhere inside of the wall. So this slope of the temperature field to this temperature gradient is always negative 80 degrees Celsius, no matter where I try to analyze the wall. Okay? So we know these properties. We don't necessarily know the temperature of the surrounding environment. Can we find it based on just the information that we have here? And the answer is yes, we'll eventually do that. But the first thing that we have to do before we even get to that is a simple conceptual question, which is what is the dominant mode of heat transfer that's happening inside of this wall? And if you think about it in the context of the different modes of heat transfer that we discussed, right? Conduction, convection, and radiation, regardless of how primitive our understanding of heat transfer modes are based off of, our Neolithic science program that we described in the first lecture, we can still very clearly say what the dominant mode of heat transfer inside of this wall is. Because if you take any point on the inside of this wall and you try to say, okay, any point of material inside of this wall is just going to be made of solid, right, of brick. And all the points that are surrounding it are also going to be made of solid brick. And so if we consider what our, test system, the point of brick inside of it is surrounded by, it's just more solid. So we've got heat transfer that's occurring between two different or multiple different pieces of solid, right? Multiple different pieces of brick inside of this wall. And so as a result, the dominant mode of heat transfer that happens in the wall is conduction. Now that's not necessarily true if we consider a point of brick on the boundary between the brick wall and the environment. In that scenario, we now have to think about the fact that, okay, well, this point of brick is surrounded by air on one side. And so I've got a piece of solid, a little piece of brick that's surrounded by a fluid, and therefore at the boundary of this wall, you would imagine that the dominant mode of heat transfer is actually convection. Okay? Now, if you overthink it, you might start to wonder, well, this doesn't seem like a very effective way of thinking about it, because like one side of the, on the left side, that point of brick is going to have a bunch of brick. On the right side, it's going to have a bunch of fluid. So like, is it conduction? Is it convection? And these are all very, very good questions that come from the fact that our development of what a mode of heat transfer even is very rudimentary, right? It's very, very, very empirical. But that ambiguity is not something we have to worry about from the perspective of this question. Inside of the wall, what's happening is just conduction. Okay, so that answers that question. The other question that we have to tackle is, what are the heat transfer rates and heat fluxes that are happening inside of this wall, okay? And these questions sometimes have to be, phrased in a way that's a bit more subtle or a little bit more refined in order to avoid ambiguities, but we'll notice that the properties of this wall, the temperature field that we defined for this wall, makes it such that it's very easy for us to define a single heat transfer rate through the wall, and for us to define a very simple, like single value for a heat flux that's happening through the wall as well. In order to do this, we're going to have to create, or at least state, two different assumptions about how this system behaves, which look like they're pretty simple, but it's very useful for us to know that we're keeping track of these assumptions as we work through these sorts of problems. And the first assumption that we want to state is the assumption that everything in this system, the wall, the environment, everything, is in steady state. And all that means is that nothing changes in time. All right, so none of the variables that we are considering in the study of this problem, neither dt dx or TL or even this T infinity, none of these things are going to change over time. That's an assumption that we make at the start of the problem. Okay? So that's assumption number one. Assumption number two is that heat transfer is happening entirely in one dimension. And to parse that back down a little bit, all that means is that we're not going to consider that heat transfer could be happening, to or from the direction, perpendicular to the whiteboard, or that it's not happening up or down, right? That heat transfer is only happening left to right or right to left. And so these two assumptions we're going to see are going to be recurring assumptions that we can use to simplify our analysis of heat transfer problems. So this is the first time that we kind of explicitly state them and list them, but it is certainly not going to be the last time. All right, so with these two assumptions in hand, how do we attack the rest of the problem? Like, how do we construct the equations that we need to construct in order to make this work? Well, the first thing that we need to do is let's try to figure out the heat flux, okay? Because we know that the heat flux is a little bit more of a primitive quantity than heat transfer rate. So we have an equation for heat fluxes inside of walls. We're being asked to try to find what the heat flux inside of the wall is through the wall. So let's try to figure it out. And the equation that we had developed for this, the general equation, was that we said that the heat flux vector was equal to the negative of the thermal conductivity times the temperature gradient, all right? But this equation is a little bit of overkill in the sense that we already kind of know what direction the heat transfer is going to be taking place in. Remember that we assumed that heat transfer is happening in one dimension, and so as a result, heat transfer is either going to be happening right to left or pardon me, it's either happening right to left or left to right. Okay? So in that scenario, we don't actually need the vector part of this equation. We don't need to worry about figuring out what the temperature gradient is in terms of all of those partial derivatives. We can replace this with the component version, or a specific component version that we saw when we first started deriving what this equation was, which is just to say the following, that the rate of change, or pardon me, the heat flux in the x direction, right? So the heat flux from left to right is negative the thermal conductivity times dt dx. Okay? And this works just fine because, once again, we can figure out whether or not the heat flux is happening from left to right or right to left based off of the magnitude of what this number is, right? If this is negative, then it has to be going right to left. If it's positive, it should be going left to right. And so all we really have to do in this case is to plug and chug, right? Because we have the K and we have the dt dx. And if we plug these quantities in, what we wind up obtaining is just 0.6, so negative 0.6 watts per meter degree Celsius times negative 80 degrees Celsius per meter. And when we actually write down what that expression looks like, notice that there's two negatives here. So we're multiplying, and we make this dot a little bit bigger. We're multiplying negative 0.6 times negative 80. And when I actually write down what that number is, of course, the number is going to wind up being positive. And so then this is a positive 48 watts per meter squared. So let's just do a quick check to make sure that our signs worked out correctly. If I take a look at a plot of what the temperature of this wall should look like, well, we know that the temperature of the wall on the left-hand side is going to be 20. So if we say that this is x is equal to 0, we would say, oh, this temperature is 20, and then because the slope of the temperature field, right, this dt dx is negative, then we would expect the line that represents those temperatures to decay in the direction of increasing x. Okay? Just putting units in here to make sure that I'm being consistent about things. And so because the slope of the line looks like this, we would expect heat transfer, in fact, to be happening left to right, which is precisely what this is telling us, right? This is a positive heat transfer of 48 watts per meter squared in the x direction. So everything looks like it makes physical sense. And I always recommend that you do a quick check like this whenever you're working on an exercise, just to make sure that heat transfer, that the heat fluxes are going in the direction where they should be going. Okay? So we've already figured out the heat flux. We've already figured out the direction, right? It's 48 left to right. Now we have to ask ourselves, well, what is the heat transfer rate, right? What is Q? And utilizing the same assumption that we did before, which is to say that the heat fluxes everywhere on this wall are the same. So nothing changes in the y direction, nothing changes in the z direction, and then of course this heat flux is just a constant number, so it doesn't change in the x direction either. If I wanted to understand how much Q, like what is the heat transfer rate through the wall, then I have to take this Q double prime and multiply it by some area, assuming, of course, that the heat flux is constant through the wall, which we just stated it is. But the real question is, what is this area? Right? Well, we are talking about heat transfer that's happening through the wall, and so it makes sense for us to use the cross-sectional area of the wall, right? So we take the heat flux through all of the little points inside of a slice of the cross-section of the wall, we multiply it by that cross-sectional area, and then we find that the heat transfer rate through the wall at, any little slice of wall that we consider is going to be 480 watts. Okay? So each little point of this wall has a heat flux of 48 watts per meter squared. And if we take those heat fluxes and integrate them or add them up or just multiply by the cross-sectional area, we find that every slice of wall has a heat transfer rate of 480 watts through it. All right? So that answers the second question. Now, we still have to try to figure out how we find the answer to this, right? What is T infinity? But before we even get to doing that, I propose to answer something else. We can ask ourselves, how much energy is lost from the room over 24 hours under the previous assumptions? So if the temperature of this wall is kept at 20 degrees Celsius, if the slope of the temperature field inside of the wall is -80, we can ask ourselves, okay, well, thermal energy is flowing through the wall left to right. So whatever's over here on the left has to be losing thermal energy, right? Or at least there has to be thermal energy flowing out of it, okay? So we can ask ourselves how much energy is being, transmitted, the net amount of energy that's being transmitted through this wall over 24 hours. So maybe more precise to write down transmitted, okay? How much energy flows from the left side of the wall to the right. And all that we have to do here is, if we wanted to be precise, we could create kind of a control volume around the room. We could treat this like ambiguous room area here on the left as a physical system, and then we can consider, okay, well, we're losing some amount of energy in the form of a heat transfer rate, and try to do an energy balance off of that. But it's actually much more simple. All that we have to do is just say, okay, if we know that this wall is transmitting 480 watts of thermal energy from left to right, how much of that energy is going to be transmitted over 24 hours? Well, all we have to do is just multiply this rate over that amount of time, right? So the energy loss is just going to be for the 480 watts that we already found times 24 hours. Now, we could just multiply this and get 480 times 24 watt hours. But remember that a watt is a joule per second. So it actually makes more sense to convert these 24 hours into seconds and then use that. And so if we do that, this number becomes considerably larger, right? So we're going to convert the 24 hours into seconds. 24 hours is approximately 86,400 seconds. And so the energy loss that we find over a period of 24 hours is 41.47 megajoules, which, for context, if you're not super familiar with what the term mega means, this is just 4.147 times 10 to the 7 joules. And so the crazy thing about this is that a system which looks like it's relatively innocuous, right? It's just a wall that is, capped at 20 degrees Celsius on one side. Over time, the amount of energy that you lose seems to be like a large number. I mean, once again, we don't really have a good understanding of what large amounts of energy or small amounts of energy are, because we don't really have a context for what a megajoule is. Like, is that a large amount? Is it a small amount? But more importantly, what's happening is that there's a constant loss of energy from whatever's on the left-hand side of this wall that's happening as a result of the fact that there's this temperature imbalance and therefore a heat transfer that's occurring. So whatever is on the left-hand side of this wall, a room or whatever, that room has to be injecting energy such that this heat transfer can continue to occur in the form of 41.47 megajoules every day, right? Or a constant rate of 480 watts, which is kind of interesting to think about, right? But it's exactly the same sort of thing that we saw in the previous exercise for the human body, which is that the human body needs to create thermal energy in order to be able to sustain a constant temperature difference, which is exactly what's happening here. And so now the last thing that we want to do in this exercise is precisely to ask ourselves, what is that temperature difference, right? So we know the temperature on the left-hand side of this brick wall, but we don't know the temperature of the environment. So can we find it? And the answer is yes. Now, we have all the information that we need in order to find the temperature of the right-hand side of the wall. Okay, so let's call this TR, okay? It might not look like it, but we already have all the information. We don't even need to consider the heat fluxes that we found in part 2 or 3, okay? At least not for now. And the reason for this is because we have this information about what the temperature field inside of the wall looks like, and that information will be enough, all right? So as a reminder, I'll write it down here. Our end goal is to try to find T infinity, right, the temperature of the environment, but in order to do that, we first have to find the temperature of the right-hand side of the wall. So how do we do it? Simple calculus. So remember that we had said that dT dx was equal to minus 80 degrees Celsius per meter. Okay? But if this is true, who's to say that we can't take this statement, which technically speaking looks like a differential equation, and integrate it, right? What makes us say, okay, well, if I know that dT dx is equal to minus 80, why can't I just integrate both sides with respect to x and wind up saying that the temperature as a function of x inside of this wall is just equal to minus 80x plus some constant. Now I'm playing it fast and loose with the units. This 80 is just in 80 degrees Celsius per meter, and this x is implied to be in meters, right? So we'll make sure that it's written down in meters. And so this solution to the differential equation tells us what the temperature profile inside of this wall looks like, except for the fact that we don't necessarily know what C1 is, right? There's some constant that shows up as a result of the integration process that we haven't determined yet. Can we determine it? Sure. Because we know information about what the temperature is at a specific location on the wall. That is to say, whenever we go to x equals 0, right? Whenever we go to this left edge of the wall, whenever x is equal to 0, the temperature has to be 20 degrees Celsius, right? So T at 0 meters has to be equal to 20 degrees Celsius. And if we consider how that works, that will tell us what the value of C1 is, right? Because what happens if I replace x in this expression with 0, what am I going to find? Well, this is just minus 80 times 0, so it's just 0. And then plus C1, and then this has to be equal to 20 degrees Celsius, but you get the point. And so as a result, we already have, just from this boundary condition, right? So from this condition that we establish on the temperature profile at the boundary, we can already determine that C1 is equal to 20 degrees Celsius. And so as a result, we now know everything we need to know about what the temperature profile is in this wall. We can figure out exactly what the temperature is at any point on this wall by simply substituting the x value, right, the distance from the left edge of the wall that that point is at, okay? And so this we can use to figure out the temperature of the right-hand side of the wall very, very easily, because all we have to do is just to substitute this x with 0.25, right? So if we want to figure out TR, pardon me, if we want to figure out TR, all that we're doing is we're just determining what the temperature is at 0.25 meters, okay, which is just minus 80 times 0.25 plus 20. So, relatively easy. Of course, from the negative 80, we expect the temperature to drop as we go from left to right. That's what the negative there is doing. Okay? And if we actually go through the process of writing down this calculation, what we'll find is that TR is just 20 minus 20, which is equal to 0. And so TR is 0 degrees Celsius. So that gives us the answer to that. Is TR the same thing as T infinity? Think about that for a second. Is TR, so did we solve the problem? Is TR the same thing as T infinity? And the answer is no, actually. At least not from the perspective of the paradigm that we use to develop how heat transfer occurs between two different objects. There's no reason that this ambient surrounding temperature, T infinity, has to be the same as the temperature of a point on the boundary. In fact, if that was true, right, so if TR was the same thing as T infinity, what we wind up finding is that there's no heat transfer that happens between the wall and the environment, right? Because the delta T between the environment and the points on this wall would be 0. And so even though we can convincingly find what this TR is, we actually don't know what this T infinity is. So how would we find it? We'd actually need an extra piece of information. Because even though we talked about the properties of the wall, we haven't actually talked about the properties of the environment. And there's one key property that we need to use or find, and that property is the H, okay? The heat transfer coefficient between the wall and the environment. And so let's suppose, for simplicity, that we have an H of 1 watt per meter squared degree Celsius between this right-hand side of the wall and the environment. Can we try to use this to figure out what the heat transfer, not just the heat transfer, but what this temperature is? Well, let's just try to set up the equation that we would use to solve this problem and then figure it out from there. And the equation that we use to model heat transfer between two different objects is just Q double prime is equal to H times delta T. Now, technically speaking, we know the differences in temperatures, although actually we don't know the differences in temperatures because we don't know what the difference between TR and T infinity is. So pardon me, we don't know the differences between temperatures, okay? We know the H, but we also don't necessarily know what this Q double prime is. Is the Q double prime that's associated with the convective heat transfer that occurs between the wall and the environment, is that heat transfer, is that heat flux the same as the heat flux that we found inside of the wall via conduction? And the answer is yes, but it requires a little bit of subtlety to figure it out. So how do we do it? Well, let me draw a little schematic of our wall, a very simplified schematic of it. And let's suppose that I wanted to study a region of space that enveloped some random piece of the wall, that its right side is right on the boundary of the wall between the environment, but the left side is like inside of the wall. Okay? And there's nothing that says that I can't do this, because I'm not necessarily saying, oh, this is somehow different from this. I'm just saying I want to study how heat transfer occurs inside of this specific region of space. Okay? And if I do this, then I can set up the same equation that I had set up before to account for the different kinds of energy changes that occur inside of this region of space. Okay, which is, what is the rate of change of the energy inside of this thermodynamic system that I've created of this like half wall, and saying that that rate of change has to be equal to the amount of energy that flows in minus the amount of energy that flows out. And by the way, I'm talking about rates, right? So it's the rate at which energy flows in, or the rate at which energy flows out, plus the rate at which we generate energy. So the rate at which energy is changing inside of this little region of space has to be equal to the amount of, or the rate at which the energy enters, minus the rate at which the energy exits, plus the rate at which the energy is generated. Now, is there volumetric, thermal energy generation inside of this problem? No, this is a regular, nice, old brick wall. Okay? Nothing is happening in here. So there is no internal energy generation inside of this little piece of wall. Similarly, because the system is in steady state, the thermal energy of this region of wall doesn't change because the temperatures don't change, right? We found an expression for the temperature profile. That expression does not vary in time because we assumed that it wouldn't vary in time when we started working with the problem. And so as a result, this is also zero as well. And so all that we have to consider is that the energy that's going in to this particular region of space has to be the same as the energy that's going out. So what is the energy, or what is the rate of energy that's coming in? What is the source of thermal energy that could be flowing into this particular piece of space? Well, remember that there's a conductive heat transfer process that's occurring on the left-hand side of this wall. We had already figured out what the number for that was. Okay, so we know that on the left-hand side, we have conduction, thermal conduction, that is bringing in energy from this side of the wall to this side of the wall at a rate of 480 watts. Okay? And if this equation is to be believed, which it should be, however much energy is being brought in via conduction has to exit somehow this system. And how is it going to exit? Via convection. And so the whole idea is that if we think of the process of feeding energy into this wall as being thermal conduction, that energy has to then go and exit via convection off the other side, right? And the implication there is that the heat transfer rate, is that the heat transfer rate that we found conductively that's happening inside of the wall, this 480 watts, has to be exactly equal to whatever the heat transfer rate via convection is on the other side of the wall. Okay? And so we have a very satisfying conclusion to this sort of thing, which is to say that the conductive heat transfer rate in the wall is the same as the convective heat transfer rate at the edge of the wall, which is all just 480 watts. So can we actually finally get to the answer? And yes, now we can do it. Because in the same exact way that we can say that QCond and QConv are 480 watts, we can take the same argument, knowing that heat fluxes everywhere on each of these surfaces have to be the same everywhere, right? We assumed that that would be the case. And we can also say that, well, now the heat fluxes anywhere on this little patch of surface in the brick wall have to be the same as the heat fluxes at the boundary. Okay? And just as a reminder, we had found that the Q double prime, right, the heat flux from conduction, was 48 watts per meter squared. And so the convective heat transfer rate, the convective heat flux has to be the same as the conductive heat flux, which is just 48 watts per meter squared. All right, and then this is the thing that will get us to what we need. Because if we say, okay, when we model convection, when we model convection, we usually say Q double prime is equal to H times delta T. Well, once again, we don't know what the delta T is, but we now know what the Q is. We know that this, or the Q double prime, we know that this Q double prime is just 48 watts per meter squared, which is going to be equal to 1 watt per meter squared degree Celsius times delta T. And so we can solve for the delta T and determine that delta T to just be 48 degrees Celsius. So this is quite a shocking result, which is that the difference in temperatures between the wall and the environment is 48 degrees Celsius. And so because we know that TR is equal to 0 degrees Celsius, we can write down an equation that says that T infinity, right, the thing that we were always looking for, is just TR minus delta T, which is, in this case, negative 48 degrees Celsius. That's very cold, maybe a little unrealistically cold. But this goes to show that we can't necessarily assume that the temperature at the boundary of objects is the same as the temperature of the surroundings. Because if we hadn't, right, if we had just assumed that these two things were the same, then there's no place for that conductive heat to go. All that energy that's moving through this brick has nowhere to go. There has to be some sort of mechanism via which we can shunt off all of that thermal energy into the environment. That has to be through convection. And in order for convection to be true, the ambient temperature has to be different from the temperature of the boundary of the object. And in this case, we find that the temperature is quite, the difference in temperatures is quite dramatic, right? It's almost 50 degrees Celsius. And so the moral of the story is that both of the equations that we've developed over time give us meaningful tools that we can use to attack these sorts of problems. And that by taking those equations and utilizing, sense and judicious arguments in terms of energy storage inside of regions of space, we can actually get through figuring out what the properties of systems like these are, even in situations where we don't necessarily know if we can actually do it. So this is a very long example, mind you, but a complete, concise example that tells you how to use these equations. So we'll tackle more examples of this type later on, but we also have to start thinking about how we are going to extend our understanding of how heat transfer occurs in systems that don't change over time, and then think about how heat transfer occurs in systems where we do actually observe temperature changes over time, right? So far, we're still in easy mode, and we'll start dealing with the difficult transient stuff very, very soon. But in order to do that, we have to develop an equation to be able to do that, and we'll take a look at that equation very, very soon.